Wonderful. Good morning, everybody. I hope you're keeping well. So today's webinar is all about Odqa and about our simple but bold mission, creating industrial heat from sunlight. We talk to customers across a range of different industries about industrial heat and about our technology that's creating incredibly high temperatures from sunlight, this novel concentrated solar thermal technology. And today we wanted to focus on a few different things. One, zero carbon heat that comes from sunshine is, by its very nature, no carbon. Industrial heat is the sort of climate elephant in the room in a lot of discussions that we have. Industrial heat accounts for 20% of global carbon emissions, i.e. 1 in every 5 tons of carbon that is emitted comes from industrial heat. We also have a solution that secure energy security is really kind of top of the agenda for a lot of big businesses, and it's in the news on a daily basis, be it the oil or gas prices with everything that's going on in the world right now. Equally, fossil fuel price volatility is not necessarily new. We have COVID, Russia, Ukraine, Venezuela, and now just the latest issues with the Strait of Hormuz. So energy security is kind of always on the agenda for large corporates, but certainly is at a particularly key focal point right now. And also low cost. There's a lot of decarbonisation options which are more expensive than the existing alternatives. In our view, the only way that decarbonisation is really going to happen at scale is by meeting and beating the cost of the alternatives. So today's webinar will focus on our technology that we think can deliver a package to hit all of these factors. A zero carbon solution that's secure and low cost. It's a synthetic flame for industrial processes. So first of all, I wanted to talk a little bit more about those 3 drivers. So first of all, cost. Fossil fuel pricing is very volatile, as I said. There's an awful lot of world events that have driven volatility in fossil fuel prices. If we look at the alternatives to fossil fuel, electrification is expensive. It's at least twice the cost of fossil fuels, whereas we have a roadmap to build to cost parity with fossil fuels to really help drive adoption. Decarbonisation, industrial heat, as I said, accounts for 20% of global emissions, and it's extremely hard to decarbonise. It's a hard to abate sector. And to put the 20% in context, all of transport, that's all of aviation, all of shipping, all of land transport, accounts for around 18% of emissions. So industrial heat is bigger than the whole of the transport industry in terms of carbon. We also have government regulation that's pushing hard on industry to decarbonise, and industry has also set its own targets, and this necessitates a deep level of decarbonisation. And then energy security. Unfortunately, we have a world full of conflict. There's lots of discussion about sovereignty of energy, about security of energy, and securing supplies is a top priority for industry. And it's also a top priority for governments around the world. And that means energy security from 2 perspectives. Security in terms of moving away from fossil fuels. If we have a look at the vast majority of the world, 74% of the world are in countries that are net importers of fuel. So they're reliant on others to bring the fossil fuel into their markets. And also independence from the power grid. The power grid is, or rather there's issues with the power grid from the point of view of grid constraints. If you're a large industrial user and you're trying to connect to the power grid, you're competing with new connections for solar, new connections for wind, new connections for batteries, and now new connections for data centers as well. And industrial heat is at such a large scale that you need a huge amount of grid connection if you want to decarbonize all of your heat. So we want a solution that's not reliant on fossil fuels, and we want a solution that's not reliant on new grid connections in order to decarbonize. And today, 70% of industry heat is still provided by fossil fuels. So that's to put the problem in context. Industrial heat is a big issue to solve, but it's an issue that we think we have a really clear solution for. So let's talk about what that is. We have a solution that uses mirrors to concentrate concentrate sunlight. And this is a decades-old technology. Using mirrors to track the sun and produce a concentrated beam of sunlight is time-tested, proven, and has been done at scale in many places. The novel step that we have is this step 2. We have a proprietary receiver. It's a technology that nobody else has done before. It's an air-based receiver that can rapidly heat air up to 800 degrees is what we have proven at scale in the field, and up to 1,200 degrees, which is proven in our lab here in Oxford. Talking of Oxford, the reason that we've been able to create this breakthrough technology, this proprietary receiver technology, is because we're a spin-out of the University of Oxford, and more specifically, we're a spin-out from the University of Oxford Thermofluids Institute. This is an institute that has a real track record of commercializing IP, particularly in the world of jet engines or gas turbines. So the Thermofluids Institute does a lot of work with Rolls-Royce, for example. The problems that they're looking to solve are dealing with gas flow, and in particular, very, very, very high temperature gas flow. So we've been using their toolbox that we use to develop jet engines and applying all of that knowledge and that decades of experience to how can you create hot air from sunlight. So we use a field of automated mirrors to track the sun. Like I said, this is a proven technology. We add our intellectual property, which is our proprietary receiver, and we can use that sunlight to rapidly heat air to 800 degrees to more than 1,000 degrees. You can also store that air very easily and very cheaply. We have a brick-based thermal energy storage design. Think night storage heaters, but on a much bigger scale. We can then take that heat and we can discharge it into an industrial process. And you can either bring that directly into the process, or you can hybridize. So you could hybridize either with an existing gas burner, you could hybridize with electricity, and that would allow us to provide a much lower cost solution as a stepping stone. And in particular for industry, it allows us to de-risk that first implementation as well. We have proven already our ability to integrate with a rotary dryer, and we'll get onto a bit more detail in a few minutes' time. But there's many, many different processes that we can integrate to, and we can use this heat for. So we describe it as a synthetic flame. We're using the sunlight to generate hot air, which is used as a synthetic flame for any industrial process. And this is not just pretty slides. Like I said, this is proven in the field. If we start from the bottom left-hand side, we have a solar simulator in our Oxford laboratory in the UK, where I am today. Unfortunately, the sunshine in the UK is not so reliable, he says, as he looks out at quite a dark sky outside. So we've built a solar simulator that can create very, very, very high concentration sunlight, and it means that we can rapidly iterate our technology at a small scale and be able to develop this for different industrial processes in a very quick manner. In our solar simulator, that's where we've proven up to a 1,200 degree output temperature. We've also scaled this and put this in the field. So in the top right-hand side, there's a picture of our pilot plant in Almería in Spain. This has proven an 800 degrees centigrade output temperature from the plant, and we've taken that hot air down the tower into a thermal energy storage and also into an industrial process. We've taken it into a rotary dryer, which you can see in the bottom right-hand side. This is a typical dryer that's used in many different industries. It's used for drying sand, it's used for drying and calcinating mining materials. So this is where you might bring something out the ground and you just need to physically dry it before shipping it, or you need to calcinate it. You need to process it in order to take a step towards your end product. And typically these are huge users of energy. They'll often burn natural gas, or in very remote sites, they'll burn heavy fuel oil. Effectively, they're burning diesel in very large quantities in order to generate heat. And for a remote site, that's also very expensive. You're importing the fossil fuel, you're transporting it a huge distance to your mining or metals operation, and then you're burning that fuel, whereas you could be taking the sunlight. This demonstration is a world first. It's a huge technology leap for concentrated solar thermal. This is the first time that we've ever seen an end-to-end demonstration of generating superheated air and directly using that for an industrial process. So you can say that we really have a technology that's proven end-to-end at this pilot site. The stage of our business now is that we're looking at and having multiple conversations about deploying this in the field at commercial sites. And our real focus is on mining metals, cement, and ceramics. And we can touch a little bit more on some of those applications today in this webinar. So the first example is gypsum. As I said, at our pilot site, we have a rotary dryer. We've proven drying of sand. We've proven drying of phosphate rock. But if you take gypsum, there's a number of heat processes, all at different temperatures, that our technology is very, very suitable for. So first of all, there's the drying process. You take the raw gypsum from the ground, which you need to dry ahead of doing anything else at relatively low temperatures. Then there's a calcination step, which is at a higher set of temperatures, which is done in a furnace. Very straightforward to bring hot air into that rather than burning fossil fuels. Then there's a process to take those elements, bring them through, create and roll the plasterboard, and then once the plasterboard has been created, again, it needs to be dried before it's then shipped to the end consumer. So our hot air output can be a direct drop into existing furnaces, existing kilns, existing calciners. And as a first step, we would typically hybridize with a gas burner. That means no process redesign, reduces the risk of downtime for our first customers. Our second example is in the world of cement. Cement is a huge emitter of carbon dioxide. I think the industry just on its own is around about 8% of total global emissions. If you look at the key energy consumers for the cement process, there's preheating, and then there's also the rotary kiln. So the preheater, this is from 300 degrees to 850 degrees, and then lower down the preheating stack, it's at an even higher temperature, 850 to 900. There are multiple options for integrating to this process due to this range of temperatures, and again, likely would be a first step to have a hybridization with a gas burner, or to displace or augment alternative fuels. Alternative fuels typically being waste products that are burnt to create energy to go into the cement process. After the preheater, the product moves to a rotary kiln, and there's a process called clinkerization. This is a very, let's say, sensitive process. It needs both radiant and convective heat transfer, the flame shape and size. is very sensitive to ensure that you're getting the right product. And it's a very high temperature. It's 900 to 1,400 and above degrees centigrade. When it comes to integrating to this, even though it's a highly sensitive process, we are having discussions about how we would do this, and it does seem quite feasible. The way that we would do this is through a tertiary air feed, ensuring that both the radiant and convective heat transfer is still present in that kiln. We're able to preserve the quality of the output while reducing the amount of input, either fossil fuels or alternative fuels that are going into that kiln. And by reducing the amount of fuel, we're able to reduce the Scope 1 emissions, we're able to reduce the cost, and we're able to increase the security of supply, even for such a sensitive and very, very high temperature process. The third example that I wanted to touch on was glass. This is another incredibly high temperature process, 1,400 degrees. This would actually be similar to many metals. You can imagine melting steel, melting aluminium is also an incredibly high temperature process. Typically, there will be preheating. You don't want to create a thermal shock for your product by going straight to these high temperatures. There's also waste heat recovery from the furnace that comes into the preheating stage. So one other way to think of our technology is effectively you have waste heat that is falling on the land next to your plant. That's, sunshine that's heating the ground. You can gather that heat and bring it into the preheating stage, or you could gather that heat and bring it into the furnace, depending on the size of the plant that we're building. But again, solar heated air at 400 to 700 degrees can preheat the material directly, or we can bring it into the furnace to directly reduce the volume of gas that's being burnt for the glass industry, thereby reducing the Scope 1 emissions, reducing the cost of energy, and increasing the security of supply by decreasing the volumes of fuel that are required. And it's very much complementary to energy recovery. So it's complementary to regenerative or recuperative furnace configurations. And this is applicable, not just in those three cases, but a very wide range of industries. This slide is kind of divided by temperature band. I've showed you today some of these ultra high temperature processes like cement, like glass. I also said, we have a few discussions in the ceramics industry as well that are operating at these ultra high temperatures. But there's also medium temperatures, the 200 to 400 degrees. So we talked about building materials, mining materials. Gypsum was an example, but we've also proven drying of sand, drying of phosphate rock that would also come in this medium temperature band in this mining and minerals area. So for us, a huge kind of potential, and we're looking to talk to businesses across all these different areas who have a challenge in decarbonizing their industrial heat, who have a challenge in energy security, and have a challenge in the high cost of energy. When we have discussions with customers, we talk about why Odqa, why not do something else? And our customers have raised to us, a number of things that they're looking at. Some of them are looking at direct electrification. So taking a resistive heater and directly creating high temperature air effectively. And that is quite possible. It's a proven technology. You can create very, very high temperatures. But the drawbacks are cost. So the OPEX, the cost of electricity, is very, very high. And also grid constraints. There are plenty of sites where if you go to the power grid and say, I need an extra 100 megawatts or even 1 gigawatt connection, the answer is either no, or the answer is yes, but in a decade, and potentially at an extremely high cost in order to alleviate the grid constraint, in order to build extra lines into that plant to create that heat. The other option we hear discussed is heat pumps. Heat pumps are an excellent solution. I have one heating my house. They're superb bits of equipment, but they have a temperature cap. They're effective up to around about 200 degrees would, really be pushing the limit. So for, the food industry, food and beverage industry that's looking for lower temperatures, heat pumps are a great option. Much lower cost than direct electrification because you're borrowing heat from the atmosphere or the ground rather than directly creating the heat with the electricity. Potentially issues around grid constraints. It very much depends on the site and very much a mature technology, but it's really that temperature cap. We're looking at, customers who are trying to create heat 300 degrees and above, up to 1,500 degrees or so. There's also electrified thermal storage. So that's taking electrical heat and storing it. So that means you can create the heat at nighttime when power's cheaper. So that allows you to, turn the cost down a little bit, but there's still a capex to build that plant. And electricity is still much more expensive than fossil fuels today, and much more expensive than our solution will be also. You'll potentially still have a limit on grid constraints, and it's an industry that is maturing. It's not fully mature in the same way that direct electrification or heat pumps are today. We have had some customers talk about hydrogen. You can create very high temperatures with hydrogen. But if you think electrification is expensive, hydrogen takes it to the next level from all the studies that we've seen. There's definitely concerns about safety, be it using domestically or indeed in industry. And it's also not a mature industry. We've even talked to some customers that are exploring nuclear, building nuclear power stations just for their plant in order to move to electrification. So there's some really kind of wacky things that are being tried in the world of industrial heat. We think that our solution is quite compelling from a simplicity perspective. There's no there's no rare earth elements or materials that are required to create this. The ingredients are very simple. We need mirrors, so glass, with a small steel foundation. We need a tower made of steel or cement. We need our receiver, which is a chunk of metal on the top of the tower effectively. And then we need to transport the heat. And we do that using off-the-shelf industrial blowers and relatively off-the-shelf insulated pipework in order to bring that into a process. And then in terms of process integration, you're either injecting it at the same point that you would normally inject heat, or you're bringing it into a gas burner as a secondary or a tertiary air feed. Again, a relatively known, safe, and understood technology. So, although it's new and novel and we have a lot of IP in the way that we generate this hot air, it's also very, very simple. There's nothing kind of out of the ordinary in terms of materials, in terms of processes, and that's very appealing to large industrials who are very risk averse and whose job is to keep a plant up and running. We do have a specific geographic focus. Effectively, this is the most economically efficient in very high solar resource areas. So this is a map of the world, and it's depicting the DNI, the direct normal irradiation. In order to make our plant work, we're looking for an image of the sun. Effectively, we're looking to directly project an image of the sun onto the receiver to create the heat that we need for industry. So our operating band runs from Spain south, effectively. Unfortunately, the UK is not a target market for us today. Far too cloudy, again, looking out the window at the heavy cloud that we have today. But Spain, North Africa, Middle East, South Africa, Australia, South America and North America, there's a huge swathe of sunbelt where this technology is applicable. And we already have discussions across these regions about deploying the technology. And we're very open to hear from businesses in these areas that have a need for industrial heat and are looking at decarbonisation pathways for that. And typically, how we work with a customer is we would start with a pre-feasibility study. So there's really two key things that our technology needs. One, is the solar resource. We need the image of the sun that we can project onto the receiver. So we need that DNI, we need that solar load. We also need some land. So we need to be able to deploy this field of mirrors in order to generate the heat. There has to be land availability at the site in order to do the deployment. We also need a well-matched heat demand. So we need to understand the heat demand of the site, the temperatures of the site, and we can take that into a pre-feasibility study. Actually, just one note on land while I remember. We're about twice as efficient as solar PV. So if you imagine a 10 megawatt solar PV plant that's creating electricity, it's around about 25% efficient. We're about twice as efficient, so we use half the land area. So 10 megawatts of heat from us would be about half the land area of 10 megawatts of electricity from solar PV. So although we need land, it's not a huge quantity of land, certainly in comparison to solar PV. So we would start with a pre-feasibility study. This back of the envelope to say, let's look at a couple of sites. Let's look at the land availability, the solar resource, and see whether we should be having further conversations. After that, we would then move into a more detailed study. We'd move into a feasibility study. So a detailed analysis creating a basis of design for the plant. So where do these mirrors go? How far are we having to move the heat? What does the annual profile look like? The solar resource can look very, very different day to day. It can also look very, very different season to season. So we would analyze that, analyze the heat demand of the plant, and also look at process integration. So how exactly are we going to get this heat into the process? What does this look like? We would then do a first estimation of the levelized cost of heat. So how much is the CapEx? How much is the OpEx? What is the cost of capital for a customer? And therefore, what's the levelized cost of heat? And how does that potentially compare to other solutions as well? After the feasibility study, that gives us quite a detailed analysis of a particular plant. And we could then move on to a front-end engineering and design. So this is a very detailed design. Imagine precisely how much concrete needs to be poured. Who are we going to buy a tower from? Do we need to refurbish the gas burner in the process? And if so, who is doing that and when, and what does the project schedule look like? So a real detailed design, some firm quotes from suppliers, and a project schedule. That allows us to give a fixed price ahead of moving into the build phase. And then last but not least is the plant build. So we've identified the contractors that we want to use in the detailed design and engineering. And so we would move forward into the plant build and move into execution mode. And we find it very useful to run this incredibly structured process, getting more and more detailed at each stage. And that's a good fit with how our customers work. Thank you very much for your time today on this webinar. Hopefully that's given you a bit of an overview of Odqa, how our technology works, how we're able to generate industrial heat from sunlight, how we're able to do that at low cost, how we're able to be more secure than fossil fuels or reliance on the grid. And thank you very much for your time. I really hope we get to talk more about creating industrial heat from sunlight. Over to